we have three arcs of charge at various distances away from the origin. And what we're trying to do is figure out the electric field at the origin due to these three arcs of charge. You can use the equation that we already derived for an arc of charge, but just for practice, let's go ahead and derive it anyway. Again, a reminder, the electric field is going to be along this line, right through the middle or bisector of these arcs. And so what I'm going to do is integrate with respect to this line, both positive 45 and negative 45 degrees away. Let's go ahead and set this up a little bit. So what we've got here is a small region of charge within this little piece right here, which I'll call dq. And that is part of this angle, which is a small piece of the angle I'll call d theta. I'm going to write off to the side here. And that is subtecting some, or is going through a small piece of arc here, ds wide. And I don't know where to put ds. I'll put it down here, I guess. And this is ds. So to figure out what fraction of the charge q we have on that little piece, we can do this. Because we know that the relationship between arc length and radius is this, we can do this. So we know that dq is going to be the fraction of this arc divided by the whole arc length times q. Just figuring out the fraction of this length compared to the entire length. We know that s in this case is 90 degrees, or pi over 2 times the radius r times q. And so if we rearrange this, again, ds is going to be equal to d theta times r. And r's cancel, and we get this simple expression for d theta. We can then figure out the electric field. In this case, the electric field for each one of these is going to be pointing in different directions. This piece is going to be pointing along this direction due to that. But I actually only need this component here, because we know in the end the electric field is just going to be pointing along this axis, which I'm going to call x, as if I've rotated the axes along that line. I only want the horizontal component of that, which is going to be, if that's theta again, it's just going to be this dE over here times the cosine of theta to get the adjacent side, which is the part we want that's along that bisector. Plugging in dq, remember dq is equal to this whole spiel right here. We can stick that in down here for that piece here. And we can do a little bit of reduction here. We can move a pi down below. We can reduce it by a factor of 2. And yeah, we can move the d theta over to the other side. Nothing too terrible yet. Notice my limits of integration are from negative 45 degrees, negative 45 that way, to positive 45 degrees this way. So negative pi over 4 to positive pi over 4. Moving all the constants outside, q is a constant, r squared is a constant. The only thing I'm integrating is cosine. And of course, most of you would realize, oh yeah, I could just do a sine, or the integral of cosine is sine. Plugging in my two limits, sine of 45 degrees is square root of 2 over 2 minus a negative square root of 2 over 2 is basically 2 times square root of 2 over 2, which is just the square root of 2. So here is the electric field due to that one arc of charge that would be pointing along that line. We have 3 arcs. So what do we need to do? I'm going to use this single equation 3 times. And so we've got this expression. Let's use it. Just plugging in, all we got to do is change the charge and the radii for each of these. And again, we're going to actually use the radii and charge that's given. Microcoulombs 10 to the minus 6th. So our first ring is just q, so 2 times 10 to the minus 6 over the radius 0.1 meters, or 10 centimeters. Our second one is 4q, but negative 4, so negative 8 times 10 to the minus 6, and the radius is twice as big, so 0.2. And our third one is 9q, so 9 times that, 1.8 times 10 to the minus 5th over 0.3 squared. If you run those numbers, you get this. Notice something interesting. The first two terms are exactly equal to each other, but opposite magnitude. What's going to happen here? These two are going to cancel. What is the net electric field? It is this, and the direction would be along this bisector pointing this way. So the magnitude is that. The direction relative to the positive x-axis, you can either say negative 45 degrees or, adding it all the way around, positive 315 degrees. Either one of those would be perfect. Hopefully that made some sense. See you soon.